Introduction to Bandwidth Control. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we will explore how to use iptables for bandwidth control in router settings. Bandwidth control is essential for managing network resources, ensuring fair usage among users, and preventing network congestion. iptables provides a powerful framework for implementing traffic shaping policies directly at the Linux kernel level. Understanding how to configure bandwidth limits with iptables is crucial for system administrators and network engineers who need to manage network resources effectively. This knowledge helps in maintaining optimal performance while ensuring that critical services receive adequate bandwidth. What is iptables? Before diving into bandwidth control, it is important to understand what iptables is. iptables is a command line utility for configuring the Linux kernel's packet filtering rules. It allows you to create rules that determine how packets are handled as they pass through your network stack. These rules can be used for firewalling, NAT, network address translation, and traffic shaping. For bandwidth control specifically, iptables works in conjunction with the traffic control TC subsystem, which provides more granular control over packet scheduling and queuing. iptables itself doesn't directly limit bandwidth but can mark packets for further processing by TC rules. This marking system allows you to categorize traffic based on various criteria like source IP, destination port, or protocol. Understanding traffic control TC. To implement actual bandwidth limiting, we need to use the traffic control subsystem, commonly known as TCTC, as part of the Linux kernel's networking stack and provides a framework for traffic control. TC allows you to shape, schedule, and classify network traffic. The key components include queue disks, or queuing disciplines, classes, and filters. These components work together to determine how packets are queued, scheduled, and transmitted. When using iptables with TC for bandwidth control, we typically use iptables to mark packets that need special treatment. Then, TC rules actually enforce the bandwidth limits on those marked packets. This two-tier approach provides flexibility and granularity in network management. You can use iptables to identify specific traffic patterns, then apply different queuing disciplines and rate limiting to control how that traffic is handled. Basic setup requirements. To implement bandwidth control with iptables, you will need a Linux-based router or system with the necessary kernel modules loaded. The most important modules are NetFilter and TC. First, ensure that your system has the required kernel modules. You can check this using the ls-mod command. The essential modules include sch_htb, hierarchical token bucket, sch_tbf, token bucket filter, and cls_fw, firewall classifier. Additionally, make sure that the iptables service is running and configured properly. You will also need to have appropriate permissions to modify network rules, typically requiring root access. The setup process involves enabling traffic control on your network interfaces and configuring iptables rules to mark specific traffic patterns for bandwidth limiting. Setting up HTB queue disk. The hierarchical token bucket, HTB, is one of the most popular queuing disciplines for bandwidth control. It provides hierarchical structure and allows you to define parent-child relationships between classes. To set up an HTB queue disk on an interface, we use the TC command. The basic syntax is TC queue disk add dev interface root handle 1:HTB default 30. This command adds an HTB queue disk to the specified interface with a root handle of 1. The default class is set to 30, which will be used for traffic that doesn't match any specific rules. The root queue disk defines the overall bandwidth allocation and provides the hierarchical structure. Each class within this hierarchy can have its own bandwidth limits, priority, and queuing behavior. Creating classes for bandwidth allocation. After setting up the root HTTP disk, we need to create classes to define how bandwidth is allocated. Each class represents a portion of the total bandwidth. We typically start by creating a class for high-priority traffic, for example, VoIP critical applications, with higher bandwidth allocation. Then we create classes for regular traffic with lower allocations. For example, TC class add dev ETH0 parent 1 class 1D1 1 HTB rate 100 megabit seal 100 megabit. This command creates a class with ID 1:1 that has a rate limit of 100 megabits per second and a ceiling of 100 megabits per second. The rate defines the guaranteed bandwidth, while the ceiling defines the maximum burst allowed. Marking packets with IP tables. Now we use IP tables to mark packets that should be handled by specific classes. This marking process is crucial for directing traffic into the appropriate bandwidth classes. We typically use the mark target in IP tables rules. For example, IP tables t-mangle a pre-routing S192.168.1.100J mark set mark 1. This rule marks all packets coming from IP address 192.168.1.100 with mark value 1. This mark is then used by TC to direct these packets to the appropriate class. We use the mangle table for marking. This is because it allows us to modify packet headers without affecting routing decisions. The pre-routing chain processes packets as soon as they arrive, before any routing decisions are made. Connecting IP tables marking with TC classes. To connect the IP tables marking with TC classes, we need to create filters that direct marked packets to specific classes. This is done using the filter command in TC. The basic syntax for creating a filter is TC filter add dev eth0 parent 1 protocol IP U32 match U32 0x10 XFF at 16 flow ID 1:1. This command matches packets with mark value 1 and directs them to class 1:1. The protocol is set to IP, and the match condition looks at the 16th byte of the packet, the source IP address, for a specific value. By combining IP tables marking with TC filters, we can create complex bandwidth policies that apply different limits based on various criteria like source IP, destination port, or protocol. Implementing bandwidth limits. With the foundation in place, we can now implement specific bandwidth limits for different types of traffic. Let's create a practical example with multiple classes. We will set up 3 classes. One for critical services, 50 megabits per second, one for general user traffic, 200 megabits per second, and one for background downloads, 50 megabits per second. First, we add the classes with their respective limits. TC class add dev eth0 parent 1 class 1D1 1 HTB rate 50 megabits seal 50 megabits. TC class add device Ethernet 0 parent 1 class 1D12 HTB rate 200 megabits per second ceiling 200 megabits per second. TC class add device Ethernet 0 parent 1 class 1D1 3 HTB rate 50 megabits seal 50 megabits. Each class defines its guaranteed rate and maximum burst capacity, which helps in controlling network behavior under different load conditions. Configuring IP tables rules for traffic classification. We now need to configure IP tables rules to mark traffic appropriately. This involves creating rules that identify different types of traffic and assign them appropriate marks. For example, we might want to give priority to VoIP traffic. iptables-t-mangle-a pre-routing-PUDPD port 5060-J mark set mark 1. This rule marks all packets destined for the SIP port 5060 used by VoIP applications with mark value 1. For general user traffic, we might set a default mark. iptables-t mangle-a pre-routing-j mark set mark 2. This rule marks all other packets with mark value 2. The order of rules is important in IP tables. The first matching rule is applied. Advanced filtering techniques. For more complex scenarios, we can use advanced filtering techniques to create sophisticated bandwidth policies. These include using multiple criteria for marking and implementing hierarchical rules. We can match on source IP ranges. iptables-t mangle-a pre-routing-s192.168.1.0/24-j mark set mark 3. This rule marks all traffic from the 192.168.1.0/24 subnet with mark value 3. We can also match on protocol and port combinations. iptables-t mangle APRE routing PTCP-D port 80J mark set mark 4. This rule marks all HTTP traffic with mark value 4, allowing us to apply specific bandwidth limits to web traffic. Setting up rate limits and burst control. The rate limiting in HTTP is controlled by two key parameters, rate and seal. The rate parameter defines the guaranteed bandwidth, while the seal parameter defines the maximum burst allowed. For a more conservative approach, we might set both values to the same value. TC class add dev ETH0 parent 1 class 1D1 4 HTTP rate 10 megabits per second seal 10 megabits per second. This configuration ensures that traffic gets exactly 10 megabits per second of bandwidth with no bursting. For more flexible control, we might allow bursts. TC class add dev ETH0 parent 1 class 1D1 5 HTTP rate 20 megabits seal 100 megabits. This configuration guarantees 20 megabits per second but allows bursts up to 100 megabits per second, which is useful for applications that need bursty bandwidth. Monitoring and testing. After implementing bandwidth control rules, it is important to monitor network performance and verify that the rules are working as expected. The TC command provides tools for monitoring traffic statistics. To view current queue disks and classes, TC class show dev eth0. This command displays all configured classes and their parameters, allowing you to verify that your bandwidth limits are properly applied. You can also monitor individual packet counts and byte counts for each class. TCS class show device eth0. This shows detailed statistics, including the number of packets and bytes processed by each class, which is useful for performance tuning. Troubleshooting common issues. When implementing bandwidth control, several common issues can arise. One frequent problem is that rules are not being applied correctly due to rule order or conflicting configurations. Always check the rule order in IP tables using iptables-t mangle lnv. This command shows all rules with packet and byte counters, helping you identify which rules are matching and how often they are being applied. If traffic isn't being shaped correctly, verify that the necessary kernel modules are loaded. ls mod pipe greptc. Ensure that the queue disk has been properly added to the interface by checking TCQ disk show dev Ethernet 0. Performance considerations. While bandwidth control is powerful, it's important to consider performance implications. Too many complex rules can introduce overhead and affect network performance. Optimize by grouping similar traffic together and using efficient match criteria. Avoid overly complex rules that require deep packet inspection unless necessary. Monitor CPU usage on your router as traffic control rules can increase processing overhead. If you notice significant performance degradation, consider simplifying your rules or adjusting the frequency of rule updates. Also, be mindful of the bandwidth limits you set, as overly restrictive limits can cause user frustration, while too permissive limits may not provide the desired control over network resources. Best practices summary. To successfully implement IP tables-based bandwidth control, follow these best practices. Start simple and gradually add complexity. Begin with basic rules and expand as needed. Use proper rule ordering. More specific rules should come before general ones. 3. Monitor performance regularly. Use TC commands to verify that your rules are working correctly. Document all configurations. Keep detailed records of your rules for troubleshooting and for future modifications. Always test new configurations thoroughly in a controlled environment before deploying them in production. Conclusion. In conclusion, IP tables combined with the traffic control subsystem provides powerful capabilities for implementing bandwidth control in router settings. This approach offers fine-grained control over network traffic, allowing administrators to ensure fair usage and prevent congestion while maintaining performance for critical applications. By understanding how to set up HTTP disks, create classes with appropriate limits, mark packets with IP tables, and connect these mechanisms with TC filters, you can implement sophisticated bandwidth management policies. Remember to test thoroughly, monitor performance, and adjust configurations based on actual network usage patterns for optimal results. Thank you. Thank you for your attendance. Please consider subscribing to the channel.